Hi students, in this fourth session of Elasticity chapter, we are going to discuss bending of beams. In this session, we are going to discuss bending of beams, expression for bending moment. After the completion of this session, you will be able to know what is meant by beam, the concept of bending moment, the expression for bending moment, geometrical moment of inertia, geometrical moment of inertia for circular and rectangular cross sections. A beam is a structure of uniform cross section whose length is large as compared to its breadth and thickness. Beam can be used in horizontal position or as pillars in vertical position. These are used in the construction of bridges and in multi-story buildings. Bending moment is defined as the total moment of all the restoring couples in a bent beam. Here we consider the rectangular metallic strip as a beam, and the one end of the beam is fixed, the other end is loaded. In the bent portion, and AB are the upper layers and they are going to extend, and CD are the lower layers, they are compressed. The layers like EF, which are in the middle place, they are neither expanded nor compressed, and hence they are called as neutral layers. And divide the strip into large number of filaments of small thickness lying one above the other. In the bent position, inner filaments like CD are compressed, the outer filaments like AB are extended, and filaments like EF remain unchanged. And in equilibrium position, moment of restoring couple is equal to moment of bending couple and is called bending moment. Then consider a strip bent to an arc of a radius r. Let xy be a small part of the neutral axis and theta is angle subtended at the center of curvature O. And x dash y dash be another filament at a distance x from the neutral surface. Then the original length of the beam is xy. Then the new length of the beam is portion of the beam is x dash y dash, and xy is equal to r theta and x dash y dash is equal to r plus x theta. Then increase in the length of the filament is given by x dash y dash minus xy, and it is equal to r plus x theta minus r theta, it is equal to x theta. Then the strain is defined as the ratio of change in length to the original length, and it is equal to x theta by r theta, and it is equal to x by r. Young's modulus Q is equal to stress by strain. Therefore, stress is equal to Q into strain, and it is equal to Qx by r. Then we consider a rectangular section ABCD of the strip perpendicular to its length and plane of bending. The forces acting on the strip are perpendicular to this section, and the line EF lies on the neutral surface. The forces producing elongation are in the upper of ABEF, and those producing contraction are in the lower of CDEF. These forces are opposite in directions perpendicular to section ABCD and form a couple. Let us see that one in this diagram. And EF is the neutral axis. Above the EF are the upper layers which are going to extend. The below EF the layers are compressed, and these act as couple. And B is the breadth of the beam, and D is the thickness of the beam. Then consider a small area delta A at a distance x from the neutral axis EF. Then the force on the area delta A is equal to stress into area, and we know that stress is equal to Qx by R, and area is delta A. The moment of the force about the axis EF is equal to force into distance. The force is delta x Qx delta A by R into x, and it is equal to Qx square delta A by R. Then the moment of all the forces is given by, it is equal to Q by R into summation of x square delta A. Then let us divide the whole area ABCD into n number of parts, each of area delta A. Then the summation of x square delta A is equal to delta A into x1 square plus x2 square plus x3 square etc. to xn square. Or summation of x square delta A is equal to n into delta A. That means we are going to multiply and divide by n. Then we have n into delta A, x1 square plus x2 square plus x3 square up to xn square divided by n, and it is equal to a k square. And here A is equal to n into delta A. There are n number of small area, and hence the total area of the strip is A. That is area of the face ABCD. And k square is equal to x1 square plus x2 square plus x3 square plus up to xn square divided by n is the square of radius of gyration of ABCD about the axis EF. Then the moment of restoring couple is equal to Q by R into AK square, and it is equal to Q by R as it is, and AK square is given by IG, where IG is called as geometrical moment of inertia of the strip. And in equilibrium, moment of restoring couple is equal to moment of bending couple. It is called as bending moment. Therefore, bending moment is given by Qig by R, where Q is Young's modulus, Ig is the geometrical moment of inertia, and R is radius of curvature of the bent beam. And this geometrical moment of inertia is depending on the shape of the cross section. For rectangular cross section, we have area is equal to breadth into thickness, and k square is equal to d square by 12. Then the bending moment is equal to Q by R BD cube by 12, where d is the thickness of the beam. For circular cross section, area is equal to pi r square, where r is the radius of the circular cross section, and k square is equal to r square by 4. Therefore, bending moment is equal to Q by R to pi r to the power of 4. Then the questions of this session are: what is beam? Define bending moment. Derive the expression for bending moment. For circular cross section, write the expression of geometrical moment of inertia. And for rectangular cross section, what is the expression for geometrical moment of inertia? Then the books referred in this session are Properties of Matter by D.S. Mathur, Properties of Matter by R. Murugesan, Properties of Matter by Briswell and Subramaniam, College Physics, Volume 1, Sundarajan. Thank you.